Hello, everybody. Thanks for coming to the session. Today, we are going to talk about how San Diego Gas and Electric successfully migrated to Red Hat OpenShift Service on AWS. And with me on the stage should have been 3 speakers today. Unfortunately, both Lamont and Greg of SDG&E were not able to make it to Summit, so it will be only me presenting today. My name is Nosek, and I'm a senior container application architect at Red Hat Services. I work with both Greg and Lamont and other folks on this project. The whole migration project from start to finish took about 8 months. It means from planning the migration until the cutting off into production. The presentation today, I divided that presentation into 2 parts. The smaller part at the beginning will be overviewing the architecture which we came up with. And the second part will be discussing the disaster recovery. Please feel free to ask questions as we walk through the presentation. And I will also leave some time at the end of the presentation for additional questions. So let's start with the architecture overview. And before that, let's discuss the main objectives which we had when we were coming up with this architecture. So objective number 1 was that SDG&E wanted to leverage the managed Red Hat OpenShift service on AWS because they wanted to lower the infrastructure management effort which they had with their on-prem OCP clusters. Instead of managing clusters, they really wanted to focus their time on application development. So that was why they chose the ROSA. And second objective of this migration project was to also improve their disaster recovery strategy. We wanted to make sure that we maximize the uptime of their applications. So right away, here is the architecture which we came up with. It's sort of a minimum DR architecture. You can see that we are using 2 AWS regions. We have AWS West as our primary region and AWS East as our secondary region. At the bottom, you can also see that we still have some dependencies of our applications running on premises, especially the Oracle databases. The applications are deployed into both regions at the same time. However, the traffic is only routed to a primary region in the normal case. And in the case that we have an issue or disaster in the primary region, then we can reroute the traffic to the applications in the secondary region, so to the secondary replicas. On the diagram, you can see in the blue color depicted the workload clusters. We have multiple clusters where we run our applications. And we use multiple clusters because we want to have an isolation between different maturity of environments on those clusters. So we have a lab cluster for just where we initially deploy the application and do some testing. Later, we are promoting into stage. And the last promotion goes into production. We definitely wanted to have a separate production cluster to ensure isolation from everything else. On the diagram, you can see that the clusters, the prod and stage, they are coming in a pair. And we needed the pair of stage clusters as well as prod clusters because for the stage clusters, we wanted to be able to test our DR procedures outside of the production. So that mandated that we had to have another pair of clusters in addition to production, and that is the pair of stage clusters here. On the diagram in the red color, you can see the management cluster here. So this is a dedicated cluster, which is located only in the secondary region. And this cluster is running our GitOps tools, Red Hat ACM, and Argo CD. We do use these tools to manage our applications and also, deploy the applications and also manage the configuration of the clusters. The backups of this management cluster from the secondary region are going to the primary region so that in the case of a disaster in the secondary region, we are able to rebuild our management in the primary region as well. When you use GitOps, you also need to solve the secrets management, and because you don't want to store your secrets in Git. For secrets management, we leverage the AWS Secrets Manager. So we store the secrets there. The AWS Secrets Manager comes with the capability of replicating secrets between regions. So we can be pushing our secrets into the primary region And then from there, they are automatically replicated into the secondary region as well. On our clusters, we use the external secrets operator to pull the secrets from the AWS Secrets Manager and create them as Kubernetes secrets on the clusters. Now, each cluster is only connecting or contacting the AWS Secrets Manager in the same region as the cluster itself. There is no cross-regional communication just to pull secrets. Now, let me run through some disaster scenario. So the idea here of this architecture is that normally we operate in the primary region. It means the application traffic is going to the primary region. If we have a failure there, then we can leverage our management tools to execute the failover to the secondary region. That means we can scale out the applications in the secondary region, and we can also reroute the traffic to the secondary region. So that makes us work after the failover. In the case that there is an issue in the secondary region, then the primary region where the applications are normally running is not affected at all. And so we are happy operating in the primary region. The only thing is that if we need the management plane, then we need to just rebuild it in the primary region. So that's the scenario where secondary region is having issues. They don't really affect the applications. They only affect our management plane, which can be rebuilt. While we were building this architecture, there are several good practices which we used. First, it was important to us to talk with the teams which actually own the dependencies of our applications. For example, team which manages Oracle and team which manages other services. We had to understand how their disaster recovery strategy looks like. And also, we wanted to make sure that when they are failing over, that we are still able to connect our applications to their databases and to their services so that the applications, of course, will be still running. So it's important to communicate across teams because the application is not really running in the vacuum, so you also need to go after the dependencies. Second good practice was that we try to keep everything simple, and if we need more complexity or achieve something more, then iterate from there. You saw it on the diagram that we really use just one Argo CD for the whole architecture. It was possible for us because the team which is managing the applications as well as managing the cluster configuration is the same team, so we didn't really need a separate Argo CD just to, for example, for the sake of security, have two different instances for two different teams. And also, at the scale we are operating with some 6-7 clusters, a single Argo CD instance is actually performing enough to be able to manage everything on those 6-7 clusters. In the case that in the future we need to grow the environment, we can of course go to the model where we may use one Argo CD per cluster. That will of course increase the complexity as we will be now managing multiple Argo CDs. And the last good practice here I would like to mention is the architecture decision records, which we were making while working on the architecture. It is important when you are making design decisions along the project to actually write down what were the pros and cons of alternatives you were comparing, and also what was the final decision and why you made it. Because as the project goes and it's longer, eventually you will forget while you make certain decisions, and also the reasons for decisions are also changing in time. So later on in the project, you will realize that things changed, and you would like to be able to go back and reevaluate your existing decision and maybe change some decisions. So it's easier to do when you keep your architecture decision records with you. So now let's start discussing the disaster recovery strategy. And let's start first with the objectives. So what were the requirements we had? What were the expectations? What did we want to achieve? First, we were focusing on protecting our applications, because applications is what generates the revenue, right? You always want to start from the application and think about how to maximize the application uptime. Now, it is less important to us if the control plane on the OpenShift clusters or other operators are working or not, because if it doesn't affect the application, it's not really a disaster for us when they don't work, because you can always repair them. As long as the application is up, it's all good. So focus on applications. Now, when you are working on disaster recovery strategy, you will also need to, for your individual applications, determine what is your recovery point objective and recovery time objective. You will need to do it for each application. Maybe you will divide your applications into different tiers based on what those objectives are. So the tier 1 applications are the most critical, and they need to be recovered the fastest and with the most data not lost. And maybe the tier 3 application can be recovered only later or can take some time to recover it. That's fine. So the recovery point objective is telling you the maximum amount of data that you are willing to lose during a disaster, due to a disaster. So for example, if you are fine, and it depends on the application, if it's fine for a given application to lose even several hours of data, maybe the whole 24 hours of data, then for that you will be fine with doing periodic backups and restoring from the backup. That's a fine method how to achieve this objective. On the other hand, if you have applications which are more critical and can, for example, are able, or you allow them to only lose minutes of data, then you are already looking at using asynchronous replication. And if you cannot lose any data, even during the disaster, then you need to replicate the data synchronously, because that's the only way how you can make sure that even when the disaster happens, that you still have the data. Now, regarding the recovery time objective, RTO, that one describes the maximum acceptable length of downtime. It means it actually describes like how much maximum time it can take for you to bring the application back up after a disaster. And this time includes the things like you need to recover the data maybe from the backup. You need to scale the application up if it was downscaled. And you also need to reroute the traffic to the application so that actually the application users can finally see the application up and running and can use it. So that's your RTO. Again, RPO and RTO are important because unless you in the team agree on them, you only from there you can really be designing the same design to achieve those objectives. Otherwise, everybody is working on slightly different problem. Another objective we had for our disaster recovery was that we wanted to protect against data corruption or deletion of data. And this could happen really by accident due to a human mistake where I go to the database and delete some rows. Or it can happen due to software issues where the new version of the application unfortunately starts corrupting the data. So to protect against data corruption, it doesn't really help when you use replication. That you replicate between regions doesn't really help you because the replication exactly replicates the primary replica. And so the corrupted data will be just replicated into the secondary region, and you will be corrupted on both sides. So what really helps against data corruption or accidental deletion is to do data backups and then restoring from backups. In our example, we used the Valero operator to back up the AMQ streams, Kafka queues on the cluster. And the last objective for our disaster recovery is protecting against infrastructure failures. So when you want to protect against infrastructure issues, you pretty much need to use redundant infrastructure. So that means in our case, it was it was running across multiple availability zones in the region, and even because we wanted to protect against regional failure, running across multiple regions. In our case, we chose 2 regions to keep the cost down. As soon as you use redundant infrastructure, you will need to start replicating data because you, of course, need to have the data on all your replicated infrastructure. And also, you will need to figure out the traffic management because now you need to be able to route the traffic into the primary infrastructure, but then also reroute to the secondary infrastructure in the case that the primary has issues. So let's discuss more in depth the protection against infrastructure failures. And for that, there is a good description in the AWS well-architected framework. And this framework proposes several different architectures which we can evaluate for your own solution. The basic division here is that they have active-active and active-passive approaches. So the active-active is an approach where both regions are actually serving the application traffic. So that means there is no failover from one to the second one, but actually both regions are actively serving application traffic. Now, for that, you pretty much need to have the application already designed with the idea that you will be using it in an active-active mode. Especially, you need to make sure that the data replication works well enough, that the data is available in both regions at the same time as the users are coming. So for our case, because we were migrating applications where the design was really not thinking about active-active usage across regions, we had to go with the second option here, which is the active-passive. With the active-passive, you are routing the traffic only to a single region at a time, and the second region, the secondary one, is just running the application but receiving no traffic, so it's a passive region. Now, regarding the active-passive, there are 4 different approaches which are described in the AWS well-architected framework, and those are the backup and restore, the pilot light, warm standby, and hot standby. Now, they differ in a way that the approaches like hot standby provides you with a fast recovery. However, it also costs you more to deploy it that way. So let's now dig into these 4 different active-passive approaches. So let's start with the backup and restore. On the left side, you can see a diagram which is showing the normal operation. And we have 2 regions. One is active and one is standby. The traffic from the users is routed only to the active region. Now, the standby region doesn't have the application running at all, and instead, we are only making backups from the primary to the secondary region. So this is a cost-effective solution because you are not really paying for a compute in the standby region. Now, in the case of a disaster in the primary region, what we need to do is, from the backups, we will need to restore the application data. And then we will need to also start the application in the secondary region. After that, we can reroute the traffic into the secondary region, and that now becomes promoted into the active region. So that is the backup and restore strategy. We use this strategy for our Red Hat ACM cluster, where we are actually just backing up Red Hat ACM from the secondary to the primary region. And then in the case we need it, we can rebuild it there using those backups. Second type, or second approach here is the pilot light. With pilot light, you have, again, active and standby region. But instead of just making backups into the secondary region, you are actually keeping the application services running in both regions, in the primary as well as secondary. So we use, for example, this strategy for our Kafka clusters. We do have Kafka clusters running in primary as well as secondary so that they can keep replicating the data, even when the application itself is running only in the primary and there is no application pods running in the secondary. Now, yeah.
When you make a data replication,
yeah.
Is it something like the synchronized replication or asynchronized replication?
So the question was, if we do the data replication, if it is synchronized?
Or asynchronized?
Yeah, the data replication can be either synchronous or asynchronous, and we use asynchronous one. For the Kafka, we use the mirror maker, which is an asynchronous replication. The negative part of the asynchronous replication is that, unfortunately, you cannot ensure that you don't lose any data, all right? But for us, it was acceptable. So yeah. Otherwise, if you cannot lose any data, you will need to go with synchronous replication, which has other drawbacks, like it's not that reliable because you can only write data if it's synchronized across replicas first. All right, so that is the pilot light. Next approach is the warm standby. And the warm standby is another optimization where, in addition to running the application and replicating the application data and running the application services in the secondary region, we also run a downscaled version of our application in the secondary region. So that allows us now to actually, because the application is running there, even when not in a scale which would be able to absorb the full production traffic, we can now monitor our application and see that it's healthy in the secondary region as well. So before we are then failing over, we can make sure, okay, the application is fully healthy. Now, in the case of a disaster, when we're using warm standby, what we need to just do is to scale out the application in the secondary region so that it's able to serve the full production traffic, which is a big load, and then reroute the traffic to the secondary region. And the last strategy in the active-passive approaches is the hot standby. We did use hot standby as well. Hot standby means that you are pretty much deploying the application the same way, in the same scale, into both regions at the same time. So you can see that all pods are scaled exactly the same, and of course there's replication between the two regions. And in the case of a disaster, what you need to do is only pretty much reroute the traffic to your active region, to the secondary one. So this allows you to really do a very quick failover. However, it is the alternative which is costing you the most, because you are literally running the fully scaled application in the secondary region all time, even when it is a passive region. Now, we use this strategy, especially at the beginning, because when you start enabling the DR for your applications, it is the easiest to just take the application and exactly as it is, deploy it into the secondary region as well. So it's a quick start with this hot standby strategy. Of course, you can then later optimize to go into warm standby or even the pilot light. That is an optimization where you save some cost. Also, because our application, the scale of the application, we are running the application across 3 availability zones. It turned out that for some applications, the 3 replicas running in 3 different availability zones are already able to serve all the production traffic. So pretty much just by the fact that we are running them as 3 replicas, they are already upscaled all the way to the production grade. All right, so that were next thing which I was talking about before is that when you now have, you are operating across or in 2 regions, you will also need to solve the traffic routing. In our case, we had application clients which could be deployed anywhere, be it on-premise or in the cloud. And also, we didn't really have a control of the clients. So we could not really come to the clients and reconfigure them in the case of a disaster to send the traffic into the secondary region. That was not really possible for us. So the solution which we came up with was to use the DNS-based traffic routing. And for that, we leveraged the DNS and the fact that we were able to configure DNS records. So for each application endpoint, for each application, we have a CNAME record in DNS. And that CNAME record either resolves to an IP address which points to the either primary or, in the case of a disaster, into the secondary region. And so when we want to fail over, we just need to update that DNS record. And after a while, after the DNS cache expires, the application data will be automatically flowing. Instead of the primary region, it will go into the secondary region. So without us touching the clients, we are able to reroute all the client traffic. The implementation on OpenShift Rosa looks something like this. At the top, you can see that we have our Route 53 private hosted zone. So that's where we are hosting our DNS records for our applications. And then we have an application client. The application client, before it sends a request and opens a TCP connection, it goes and resolves the name of the application. And based on that, it will receive an IP address, which is the IP address of either the ingress router in the primary region or the IP address of the router in the secondary region. After that, the client will just contact the given router and will reach out to the application. Now, if we want to fail over the application traffic, we use GitOps approach, where the DNS record in Route 53 is actually managed using a DNS endpoint resource. And this is a resource which is watched by our external DNS operator. So on your cluster, you install the external DNS operator, and then you can create DNS endpoint resources which describe individual DNS records. Here in this example, you can see a DNS record, which is actually a wildcard record. There's like the star at the front. And so it says that all applications which match this wildcard will be routing the traffic towards the ingress router in the west region. So that is our primary region. So with the one change of this line, we are able to reroute the traffic of multiple applications, all of them which match the record, which are typically all on the cluster, reroute that traffic to the other region, to the other cluster. The DNS endpoint gets updated in Git, and then Argo CD applies the DNS endpoint to the cluster, and DNS operator will take it and, based on that, update the Route 53. You can see that the external DNS operator is only deployed in our secondary region. The DNS records here are global records. It means you cannot really have multiple external DNS operators working with the same records, because otherwise you would get a conflict. So we are deploying external DNS only to the secondary region. And the idea is that in the case that the primary is healthy, we don't really need to fail over traffic. We are fine. In that case, if the secondary maybe have issues, then we are not able to reroute the traffic, but we don't really need it. On the other hand, if the primary regions have issues, then we expect that the secondary region will be OK, and then we can use the external DNS operator to reroute the traffic away from the primary region. So one thing which I didn't mention was that in our disaster recovery strategy, we are only protecting ourselves against a failure of a single region. Of course, when there is a failure in both regions at the same time, our applications will be down. That is accepted. If I go more into the detail of this picture here, then you have seen the wildcard record, which allows you to match multiple applications and reroute them all into the other region. But what we can also do is we can also create an individual DNS record. And that means that that's a record which exactly matches just one application. And so just the traffic for this one application can be routed. In DNS, when you create DNS records, and one of them is wildcard, and one of them is specific record, which matches exact the host name as the client is using it, then the DNS will actually return the IP address of the specific record. So in other words, the specific record overrides in DNS the wildcard record. So that allows us to, we for example, use this when we want to just test our failover and test the failover just of several applications at a time. We can override those several records and check that the traffic for those particular applications is flowing into the other region. Now, one point which I didn't mention on the previous picture is the routing of the traffic when it hits the cluster. So when it comes to the ingress router also needs to be able to find out where and to which pods the traffic should be forwarded to. You can see here that we are actually using these, what I call global routes. So this global route is, of course, needs to be available in both clusters. The traffic will come into one cluster of the two, but this route needs to be available in both clusters so that both clusters knows how to forward the traffic further to the pods. And so to achieve that, we are actually creating this route by creating what we call a global route, which is a route object in OpenShift. And let me compare the cluster-specific route, which is the classic route which you always create when you deploy an application to OpenShift cluster, and the global route. The cluster-specific route, we are not putting a host name here. That one is automatically generated using the route name. And this route only works for that particular cluster. On the other hand, the global route has a host specified here, and this host is the global name of the application. Now, this global route needs to be created in both clusters, in the primary as well as the secondary, at the same time, so that when the traffic comes using the global route, the cluster knows where to forward it to the pods. And with that, we can walk through the final review here. So what did we discuss today? We talked about the DR objectives. So when you are planning for your DR, you will want to focus on protecting your applications, because that is the revenue which is generated for the company, not necessarily focus on protecting the clusters or the infrastructure on the clusters. The applications are the primary focus. Also, you will want to, for your applications, determine the RPO and RTO, so the recovery point objective and recovery time objective. You will, based on these objectives, you will probably group your applications into different tiers based on how they are important for you and based on how quickly you need to recover them and how much data you can afford to lose for the given application. If you want to protect against data corruption or data deletion, then you must use backups. So in other words, you cannot get rid of backups just because you are replicating data. You will still need backups as well. And then if you want to protect against infrastructure failures, you are looking at using redundant infrastructure, for example, multiple availability zones, or in our case, because we want to protect against regional failure, even multiple regions. If you use multiple regions, you can find in AWS well-architected framework several approaches for the active-passive architecture. Today we discussed the backup and restore, which is let's say the most cost-effective approach. However, is also the slowest to use to recover. Then there is pilot light, the warm standby, and the hot standby. With the pilot light, you have your data services running in both regions, so the data is actively replicated. However, the application is down, and you just need to scale it up to start it. With the warm standby, you already have at least one application replica running, even in the passive region, which allows you to monitor your application in the passive region. And with the hot standby, you are running the application in both regions with the same replica size. And so it's prepared right away to absorb and to serve all production application traffic. Regarding data replication, there are three options. So you can replicate data using backups. That is typically done by creating a snapshot and then copying the data out from the infrastructure so that you protect that backup when the infrastructure fails. Then there is two kinds of replications, continuous replications. One is asynchronous and one is synchronous. The asynchronous one is more reliable because you don't need to fail the request of your client in the case that you cannot send the data over to the other region. So you will actually copy the data asynchronously after you already told the client, I store the data. You can only after the fact actually copy them into the other region. So that is, from the standpoint of the client, more reliable. Unfortunately, asynchronous replication cannot ensure that you will not lose any data when there is a disaster. Because it can happen that you will tell your client that I store the data, and just before you replicate it to the other side, you will have a disaster. So you lost the data in your primary region, and you cannot recover it anymore. On the other hand, the synchronous replication will not lose any data for you, because before you tell the client that you store the data, you already have replicated them in the other region and made sure that they are stored there as well. Only after that, you go back to your client and says, OK, I now store the data. So synchronous replication doesn't lose any data, even during disaster. However, it's less reliable, because if it happens that the secondary region is not available for a bit, then all your requests in the primary region to store data will be also failing, because you just cannot store them in the secondary region. So in other words, there is the two conditions, right? Primary and secondary needs to be able to store the data before you can actually store the data. We also discussed the DNS-based traffic routing. So that is one of the options, how you can reroute the traffic without having the control of your clients. That was the last point. And they asked me if you could please fill out the session survey as well. We would appreciate that. And with that, we have still 10 minutes left for any questions or comments you may have. Please go ahead.
Can you speak a little bit more to how you're using Valero and Kafka Mirror Maker to do replication? Like, what are they replicating? How are they working together?
Yeah, good question. So the question was how we are using Kafka Mirror Maker and Valero to replicate the Kafka data. We use the Mirror Maker to do the asynchronous replication between two Kafka replicas between the two regions. So that one is always there, running all the time. It's continuous replication. Allows us to quickly recover in the secondary region because the data is already there. It's just minutes before it gets there. So it's very quick. So that protects us against the case where we have a failure in the primary region. Now, regarding the Valero, we do use Valero to back up the PVCs of Kafka. So the Kafka is running as a 3-node cluster, and there are 3 PVCs. Maybe there's actually 6 of them, but the 3 ones which are holding data. I cannot remember now. So we do use Valero to periodically back up those 3 PVCs, and that backup is again uploaded into an S3 bucket in the, I think it is the opposite region. I'm not sure anymore. It is actually it's not the opposite region. We are actually uploading the backups into the same region because the goal of this backup here is to protect us against against the corruption of data, not necessarily infrastructure failure. So we use replication to get the data out of the region. We use backups to protect against corruption, and that data, the backups can stay in the same region. Does it make sense? Or?
Yeah, it does.
Okay.
How are you starting up your applications in the secondary region in the case of?
Yeah, so that's a very good question. How are we starting up the application in the secondary region? I didn't go into the details here, but it's actually not that straightforward because if I remember, the mirror maker is actually replicating data. Like mirror maker is running in the secondary region and replicating data from the primary region, if I remember. So we need to stop that replication first. The primary is having issues, so we need to first stop the replication in the secondary region because we don't want to corrupt the data when we are accessing them from like using the replication process and using actually the applications which will be eventually spinned up in that region. So we stop the replication first. So now we have a standalone Kafka, which is having the almost latest data in the secondary region. So when we have that, we can now scale up our applications, which will actually access Kafka and find the data as it is right there. And then as soon as we bring the traffic to the applications, they will start writing new data into the Kafka. And so now we have new data in the secondary region, and we are doing what we operate in the secondary region. So we need to, again, set up a replication eventually back to the primary region because we need to, of course, reconcile the data back to the primary region. So yeah, it's quite a procedure. Unfortunately, so far, these steps which I'm describing are mostly done manually. So it means somebody really needs to stop the replication by running a command and so on. But it's a procedure described in the wiki. Yeah, yeah, you're welcome. Yeah.
Can you help me fully to understand what is the reason of running Argo CD and the Advanced Cluster Manager on secondary region instead of running on the primary?
Yeah. Okay, so the question was, what is the reason we are actually running the Argo CD and Red Hat ACM in the secondary region instead of deploying it into the primary one?
And we'll add a little bit why instead of running two active Advanced Cluster Manager clusters on both regions and like with the Argo CD, you can just do it on both cluster regions.
Right, that is an excellent question. Yeah, so the question is why we don't run Red Hat ACM and Argo CD at the same time in the secondary as well as the primary region, right? Because we could have running them in the both regions. The reason here mainly was cost. We prefer to keep the cost down. You can see in the picture that we use a dedicated cluster to run these tools. And so this dedicated cluster is several worker nodes, which require compute and subscriptions. And so we didn't want to incur that cost. And for us, we decided that, okay, we will have only one replica, which needs to be then in the secondary region if you have only one, so that we can use it for the failover. So we prefer to use only one replica, and then the ability to use our Ansible scripts to rebuild if we need from, let's say, scratch in the primary region when we need it there. So yeah, the cost was the driver here.
And one short question. When you talked about data replication from one region to another, you just mentioned Kafka, but there is a plenty of applications which do not support data replication.
Yeah.
So did you have any solution for that, like using some kind of fancy file system which replicates everything to different, or active data replication was no longer with the Kafka applications which supports?
Okay. So if I understand, the question was, if the application itself doesn't support data replication, how do we solve that? Like, how do we work with applications that were not designed with data replication capabilities? So let me find actually a slide which I didn't present today, but I have it somewhere. This slide here. So the first option we were talking about now is the application, what I call here application layer replication. That means that, yeah, the application has the capabilities to replicate data. And I have examples here, Oracle Data Guard, Postgres, MySQL dump, and so on. So we always prefer to use them if they are available. If you say they are not available, then we need to go with the, what we call here, storage replication. So we are replicating on the storage layer, where the application actually doesn't have an idea about that the data under the application is replicated, but it is. And there is different storage solutions which actually can do the storage layer replication, like, for example, Ceph, Walsync, even EBS, for example. I mean, EBS volumes can be backed up into S3 while the application is running. So in other words, you need to defer to this kind of solution which is working under the application, which is not ideal because the application have no idea that something is happening, and also the monitoring capabilities are not so great because you are literally copying blocks of data without the understanding of what it has to do with the application, right? On the other hand, if you use replication like with Kafka, with application level replication, you actually know exactly like this queue, how many messages are already replicated. So you can monitor much better because it's an application level replication. So does it answer the question? Okay. All right, I'm looking, we have last 3 minutes, so maybe one question.
What about recovering back to the primary? I know you didn't cover that, but that's a big topic of whether you leverage the secondary region as the primary and switch the old primary as the secondary, right? Or if you actually move back to the primary. What's SDG&E's like?
Yeah. So yeah, the question was when you are after the disaster and you are now after that recovering back to the primary region, right? So the disaster is gone, and now you want to go back to your normal operation. Like, how do you consider your regions now? We at SDG&E, we do consider the primary and secondary region as primary is always west and secondary is east. So at least in our understanding, the primary and secondary role don't change. They are attached to the region and they don't change. So in other words, we call it, when we are operating in the secondary region, we operate in a secondary region, which is something which is not really by default, right? It's only after a disaster. Yeah, and after that, as I described, when the disaster is resolved, then you need to especially replicate the data back. So I discussed the Kafka replication, which you need to flip and turn back, but also the AWS Secrets Manager, the secrets which you may have created in the meantime while operating in the secondary region, you need to also replicate back to the primary region, which again is possible with AWS Secrets Manager. You can mark that secret as a standalone and then set the replication back to the other region. And then after that, again, right, after you replicate everything back, you need to stop the replication and turn it back again. So these are all manual procedures. We don't have it automated, but we are capable to do it. Yeah. All right. If there are no other questions, then thanks a lot for your attention today. Thank you for coming.